how do we obtain information about a population? Of course, we could ask everyone, but that would be time-consuming, very expensive, and in fact, we might not be able to find everyone. We could wait until after whatever we're interested in happens, for example, an election, and then see what happened. But of course, people typically want to know about a population in advance, not after the fact. And in fact, what people want to know and how they want to know it is as varied as the people and organizations that have need for information about the population. For example, a manufacturer might want to know about the percentage of items being manufactured that are defective, the average life of a particular thing, such as a battery, operated like a AA battery that's used in a toy. The manufacturer needs to know what the typical lifespan of that battery is. A financial institution, perhaps, would want to know the average balance in a retail account at a particular point. Or perhaps a bank would need to know what interest rate on a savings account would inspire savers to deposit more into their accounts. Obviously, a politician would not only want to know about the outcome of an election, but he or she might want to know the feelings of voters in his or her location about a particular item, or possibly what percentage of voters plan to actually vote in the upcoming election. Or most importantly, for someone who's starting a campaign, what percentage of the possible voters recognize his or her name. A municipal government might be interested in knowing the people's attitude about a certain zoning change, or their opinion of the school system, or even, for example, the response time, the average response time for a 911 call. In all these situations, and many, many more, we need to use something other than asking everyone or measuring everything to find information about everyone or everything. I guess the best example of why we don't simply measure everything would be, let's take the light bulb manufacturer who wants to know exactly what the average lifetime of a light bulb is. That is, how long before the average light bulb stops working and is no longer a light bulb. Well, we could take the million light bulbs that are manufactured in a particular time span and test every single one of them. And when we've done that, we would know exactly, to the second, the average time for the light bulb to work. The only problem is we now have a million light bulbs that were not light bulbs, and what do you do with them? So obviously that manufacturer would have to do something else, as would the politician and all the other companies and organizations that seek information about the population. What they would do is they would take a sample, and from that sampling process, make a statement about the population. Sampling can be a very effective means to obtain population information. A census, which gathers data from the entire population, is probably not as accurate as a well-designed sampling process. Many statisticians argue that a sampling should replace the U.S. Census that's done every 10 years, so we have more accurate information. The courts have ruled that the census is what should be used, not because of statistical correctness, but because of the Constitution and their interpretation of that document. The central limit theorem tells us that a sampling distribution would be approximately normal if we have sufficient sample size. We use this knowledge to interpret the sample result to gain information about the population, to make an estimate. If we are seeking to estimate a population percentage or probability, we obtain a count and the sample size from our sample. If we are seeking knowledge about a population mean, an average, we obtain a sample mean and the sample size from the sample and have the standard deviation from the population, if known. If the population standard deviation is not known, or if the sample size is deemed too small to use the Z or normal distribution, we then must use another distribution called the student T distribution. The T distribution will not be discussed in this lecture series. Our sample provides us with what is called a point estimate. So, for example, if we took a sample of those light bulbs, and the sample of 100 light bulbs lasted 83.6 hours. If someone said, what would you estimate the typical light bulb to last, we could say 83.6 hours. But we also know that there's variation in the real world, and certainly in the normal distribution, and therefore what we'd like to be able to do is, instead of saying, well, it's 83.6, but it could be more or it could be less, we'd like to say, here is an interval in which we believe the true average lifespan of that light bulb lies. And that is what we're aiming to do right here. The question is, how much confidence do we have in that interval? And the confidence is portrayed as a percentage. Typically, in most survey results you see in newspapers and magazines, on radio and television, we use a 95% confidence interval. A 95% confidence interval means that if the sampling process that was done was repeated over and over again, let's say 1,000 times, 1,000 different samples, all of the same size, all done the same way, and for each sample we obtained this confidence interval, then if of the 1,000 samples, 950 of those confidence intervals would contain the true known to Zeus population parameter. Remember, parameter is the statistic for a population. 50 of those sample intervals would not contain the true population parameter. Since 950 is 95% of 1,000, that's we get those numbers. And that's what the 95% confidence interval means. Some people would say that the 95% confidence interval means that there's a 95% probability that you know that the true population parameter is in your interval. That is just not right. The definition or explanation of the meaning of the 95% confidence interval is as just was stated. The problem is that you don't know if your one sample is among the 950 that contains the true population parameter, or your sample is one of the 50 that does not. That is why statisticians deal with uncertainty. A statistician never has to say, I'm certain, because he or she, in most situations, such as confidence intervals, cannot say that at all. You can only say it after the event has taken place. But after the election, everybody knows who's won. Everybody knows who has won. We are concerned about making a prediction before the election based on a sample of voters' attitudes. Our knowledge of the standard normal table, the Z table, and our information about hypothesis testing can help us in determining how we get this confidence interval. Basically, we are going to look at two types of confidence intervals. The first will be a confidence interval on the percentage of the population, and the second will be on the population mean. So let's take a look at how we compute a confidence interval to estimate a population percentage or probability. We obviously start with a sample p-hat, a sample proportion. And we get that by simply taking the count of people who are successes in the sample, X, and dividing that by the sample size, N. We also must get a particular Z value. Recall that in the hypothesis test, we went to the table with a Z value based on both the sample and population information. In a confidence interval, we have no population information. That is what we are seeking to estimate. So what we're going to do is use our knowledge of the normal distribution to get us that Z value. We know we have a 95% confidence, and therefore there's a 5% chance of error. That 5% is split in half, 2.5% above the interval and 2.5% below the interval. And since we have a normal distribution, the Z value that will give us that 2.5% tail is a Z of 1.96 plus or minus. The positive 1.96 is for the error above the interval, and the negative 1.96 is for the error below the interval. So now we have a Z value based on our 95% confidence interval. And now we've got to get a standard error. Recall that standard error is the standard deviation of the sampling distribution. That is the distribution of all the samples in the population, of which we've taken but one. And that standard error is sigma p hat. And you might notice, if you remembered what that formula was from the previous lecture, this looks just a little different. This has the square root of p hat q hat over n. In the hypothesis test, we had the square root of pq over n. Remember, we have no p, and therefore we have no q. That is what we're attempting to estimate. All we have is the sample proportion of success, p hat, 1 minus that, or the sample proportion of failure, q hat, and of course our sample size, n. Now we have the standard error, and we're ready to compute our 95% confidence interval. Of course, if we're using a different degree of confidence, the only thing that would change would be our z-value. If we wanted more confidence, our z would be greater than 1.96. If we wanted less confidence, our z would be less than 1.96. I've chosen to use the 95% confidence interval because it is so widely used among various organizations. So, we take our data that we have, our information we've computed, and we get our confidence interval on p. And we say that p is equal to p hat plus or minus z sigma p hat. That is the sample proportion plus or minus our z-value times the standard error. Okay, so now we have our interval. So let's take an example and look at a situation where someone will be interested in knowing an estimate, a valid estimate, for the true percentage of a population. Perhaps we suggest we go out and we sample 100 randomly selected people. And we found that 36 of them use public transportation to get to work. We could compute a 95% confidence interval to estimate the true percentage of the population who utilize public transportation to get to work. The sample proportion, p hat, is 0.36 because we have 36 out of 100. The standard error, based on our computational formula, is 0.048. We've worked it out to 2 significant decimal places. The z, of course, is 1.96. So given our formula, we have p equals 0.36 plus or minus 1.96 times 0.048, or 0.36 plus or minus 0.09. That plus or minus 0.09 is called the margin of error. We could also state this as that we have a probability of a person using public transportation to go to work as 36% plus or minus 9%. Or if you'd like, we believe that the true percentage of people who use public transportation to go to work with a 95% confidence level is between 27 and 45%. That is, we simply add the 9% to 36, and we subtract the 9% from 36. Let's go back and look at the computation because, in effect, the computational formula will tell us something very interesting about this margin of error. Because what we have, you recall, is our margin of error is plus or minus z sigma p hat. And the question comes about, a 9% margin of error is too large. What can we do to reduce the margin of error? By the way, typically in most political surveys, the margin of error is between 3 and 4%. That plus or minus 3 or 4% on either side of the sample proportion. Well, you'll notice that the z was obtained from the confidence level. And I said if you wanted a smaller z, you need a smaller degree of confidence. So if indeed you were willing to accept 90% confidence, fine. Then you would have a smaller z. In fact, that z would be 1.645. Obviously, if you wanted more confidence, you'd increase the z, which would increase the margin of error. Obviously, the one thing we definitely can control, and we might not want to change the level of confidence, is the sample size, because the sigma p hat has an n in the denominator. Making n larger makes the fraction smaller. We cannot control the p hat and q hat. That is what we obtain from our sample. but we can increase the sample size. And in fact, before we took the survey, we could go out and look at N and say, what N would we need to get the margin of error we'd like? And in fact, that's usually you'll find that most political surveys have around 1,000 people that were sampled. And that is because 1,000 people gives you approximately a margin of error between 3 and 4%. Let us take a look at a situation where we are examining a sample mean to estimate the population mean. Let us say, for example, that we go into the sample and we get our X bar, which means we add up the measurements and divide by N. We obviously have an N, and we should have the sigma, the population standard deviation. The standard error is obtained by looking at the same formula we used in hypothesis test, sigma over the square root of N. So that sigma X bar, the standard error, is sigma, the population standard deviation, over the square root of the sample size, the square root of N. And since we have X bar, and we can compute our standard error, and we know our Z from the level of confidence, we now have our formula for obtaining that 95% confidence interval to estimate the true population mean. The population mean mu is equal to X bar, the sample mean, plus or minus Z times sigma X bar. So a quality control technician tests 100 randomly selected 9-volt batteries. The sample average lifespan for those batteries is 78.6 minutes. And the standard deviation for all 9-volt batteries has been established at 18.3 minutes. We have a sample size, 100. We have a sample mean. We have a population standard deviation. If we want a 95% confidence interval, we know that our Z is 1.96. And therefore, we can obtain an estimate on the population mean mu equal to 78.6 plus or minus 1.96 times 1.83. We can say that the average life of this 9-volt battery, based on our sampling process, is 78.6 minutes plus or minus 3.6 minutes. We are 95% confident that the true useful life of those batteries produced at that factory, at least that day, is 78.6 minutes with a margin of error of plus or minus 3.6 minutes. The interval can also be written as being between 75 minutes and 82.2 minutes, obviously adding and subtracting the margin of error. Going back to the original formula, that the margin of error is Z times sigma X bar, and sigma X bar is sigma over the square root of N, we can see that once again, to control the margin of error, we can either change the level of confidence, and if we make it less confident, that is a 90% confidence interval, we'd have a narrower interval. But most likely what we're going to do is increase the sample size, which would reduce the margin of error to the level we'd like. The question comes about, why don't we increase the sample size to a very, very large number and have a very, very small margin of error? Once again, we're back to the light bulbs. In the case of the light bulbs or the 9-volt batteries, if we use up a lot of batteries or a lot of light bulbs, we have fewer to sell. So there's an economic situation there. And of course, in terms of the survey of people, to enhance the sample size, it costs money. So the politicians, the newspapers, etc., have established that a plus or minus 3 to 4%, 1,000 people, is economically viable and meaningful in terms of its information. Let's take a look historically at some interesting political surveys that taught us some lessons about what not to do when taking a survey to generate a confidence interval. In 1936, there was a magazine that was called the Literary Digest. And I believe beginning in 1920, every 4 years, they had a prediction of the results of the United States presidential election. And in fact, in 1920, 24, 28, and 32, they were very much correct. And in 36, they announced to the world, to their readers at least, that they had an even larger sampling process. They were going to sample even more people to get a very accurate prediction of the 1936 election. Of course, that election pitted the incumbent president, Franklin Delano Roosevelt, against Alf Landon, who was the Republican candidate. At the time they announced how they were going to conduct this poll, a young PhD in Iowa who had gotten involved using his statistical background to look at surveys for political purposes, decided to test the method. And he indicated that using the method they were going to use, they would make an incorrect prediction. And he predicted what they would predict. He also predicted what the actual results of the election would be. The Literary Digest predicted a landslide for Alf Landon. And of course, we all remember President Landon. You don't? Well, that's because he didn't win by a landslide. And that's exactly what they predicted, and also exactly what this young PhD in Iowa predicted they would predict. Pretty good. And his prediction was that Roosevelt would win by a landslide, which is exactly what happened in 1936. Sometime thereafter, the Literary Digest went out of business. Whether it was because they were embarrassed by this or not, I'm not sure. The name of that PhD from Iowa was George Gallup. And of course, we've all heard of the Gallup poll. He became famous and eventually became a national institution, I guess, in terms of looking at surveys and making predictions about the population. The question is, what did they do wrong? They took a very large sample, and their sample was done via mail, and they got a significant percentage of return. Typically, when you take a sample where you have people respond via mail, you get a very small percentage of the people. Well, the question comes about, how did they select their sample? In 1936, sampling techniques were still not thoroughly understood. They sent surveys to three groups of people: people who subscribed to Literary Digest, people who had automobiles registered in their names, and people who had telephones listed in their names. And what's wrong with that? It's a very wide group of people, and if we did that today, it probably would provide meaningful results. But this was 1936. I don't know about you, I know my parents didn't subscribe to Literary Digest. In fact, they probably didn't get any magazines because they couldn't afford it. And many people did not have a telephone. In fact, I can remember in the early 1950s when we got our first telephone in the house. My father, when he got a telephone call, usually was called to the local drugstore, and people would call him there, and he'd have to run down to the drugstore to answer the telephone. And of course, many people, especially people living in rural areas and in the cities, did not own cars because they couldn't afford it. This was the middle of the Depression. So what happened is, among the people that the Literary Digest surveyed, wealthy people, Republicans, Alf Landon won by a landslide. The problem was, in 1936, most people weren't Republicans. Most people were poor, and most people voted for Franklin Roosevelt. Well, Gallup, in doing his survey, recognized there was a need to look at the population and sample in a way to include all possible groups, in this case, all people who might vote. And he did that. But then came the famous 1948 election, and we've all heard about that. In that election, the governor of New York, Thomas Dewey, was running as a Republican against the incumbent, Harry Truman. Now, Truman had not been elected to office. He had replaced Roosevelt when he died in 1945. And poll after poll, including George Gallup's poll, said that Dewey would win. When Truman went to bed the night of the election, the newscasters were blaring the news: "Welcome, President Dewey." The headlines of newspapers for the next morning had banner headlines: "President Dewey." No one remembers President Dewey. He's alongside President Landon because he lost. And the reason he lost is because the determination of what was in the sample, who was in the sample, I guess, was determined by the census information. Now, in 1948, the last census had been 1940. There was some minor event that occurred between 1940 and 1948. It was called World War II. And it caused people to move Many people moved from the South to the Northeast and the Midwest to get jobs. People, soldiers who came back from the war and got the GI Bill, went to university, got degrees, and by 1948, they were living in the suburbs. But one of the real big things that happened was that unionization of workers enhanced and increased greatly. So in 1948, we had a totally different population demographics than we had in 1940. And failure to understand this, failure to use new information, caused the polls to be incorrect. And of course, there were many people at that 1948 election who really weren't sure what was happening. You also might recall, those history buffs who are watching this, that there were two major third or fourth party candidates who were running in 1948. And many people who favored segregation and states' rights, people who were exceptionally liberal and favored workers' rights, really weren't sure, should they vote for Dewey or Truman, or should they vote for a candidate who was more to their liking, who might not win. So there was a lot of confusion, and of course the results led to the very famous Truman imitating the newscaster who announced that Dewey would be president. The 1980 election, in which Ronald Reagan defeated the incumbent Jimmy Carter, provided additional information about surveying, because even the day prior to the election, the experts were saying it was too close to call. And indeed, Reagan won a rather significant victory. We saw that. Remember, we looked at the results by state of the percentage of the people in the state who voted for Carter, and there were only 2 states in the entire country where a majority of the people voted for Carter in that particular election. The reason for the lack of specificity in terms of who might win as far as a prediction was because, again, there was a significant third-party candidate, John Anderson, and many people refused to indicate for whom they would vote. But they voted for Reagan, and he won. So the idea of sampling and how to run a survey is still not a science in terms of here's how we do it, and we know it's right, and it'll be that way for a long, long time. Remember, a statistician never has to say, I'm certain, because he or she never is. Surveys and the sampling results from surveys are used all the time in our daily lives. TV ratings are really p-hats. That is, the Nielsen company goes out and gets information on a fairly large sample, about 2,000 families, and from that, the rating you see is a percentage. That is, if, for example, the rating was 14.2, that would mean that 14.2% of the Nielsen sample was watching that show. And they estimate that approximately 14.2% of the homes that had televisions would be watching that show. By the way, there's also something called a share, and that is typically the percentage of the TV sets which were turned on that were watching that show. And usually the share is important for daytime programming when many people are at work or school, and late night programming when those of us who are more intelligent are probably sleeping. But anyway, the TV companies and the advertisers use these survey results to make decisions about paying for commercials, the charging of how much money for commercials, and what shows stay on TV and what shows go off. Marketing surveys use the proportions of people who claim to be listening to a certain station or a certain program. And of course, those are marketing for the radio stations. We also market to see what products people like, what products people would like to see brought to the marketplace. And of course, we have the very famous New Coke survey, which again proved that surveying, sampling techniques are not yet a very specific science. Municipal commissions will do surveys to examine what people are interested in terms of zoning and planning issues. And colleges and many community schools will do surveys of the local population to get information about what courses they might want to offer in the evening for adult education. So, when we see a survey, we know we need to be concerned about what was the sample size, what is the confidence level, who conducted the survey, what was the sampling method, and what are possible sources of bias, which of course relates to who conducted the survey. Do we want, for example, people who manufacture cigarettes to conduct a survey on attitude of people about cigarettes? I don't think so. So it's really important to recognize many factors when you read information about a survey. Well, our next lecture, number 24, is our last one, and in that we will sum up everything we've done and see where we go from here.